Hello friends, I welcome you in lecture number 13 on series solutions. In previous lecture we have introduced Frobenius method and we have seen the method with one example, and if you recall, in that example we have introduced indicial equation. Indicial equation is a polynomial equation or quadratic equation in variable r, which is the exponent r in the assumed series solution. We start our Frobenius series solution using this form, and here r is any real or complex number, and after substituting value of this y in the given differential equation and by comparing the lowest powers of x, we obtain indicial equation in variable r, which is a quadratic equation if our differential equation is of second order. And we know that quadratic equation has two roots that we denote by r1 and r2, and there are different cases that r1 and r2 are distinct and their difference is not an integer. r1 minus r2 is not an integer. We have seen this first case in lecture number 12. Second possibility is r1 and r2 are equal, and in this lecture we are going to discuss this case in which indicial equation has two equal roots. And third possibility is r1 and r2 are different and their difference is an integer, that is r1 minus r2 is some integer. So in every case we have different criteria to write down the solution. In first case, where r1 and r2 do not differ by an integer, we assume this form of series solution and we find out this value of y for r equal to r1 and another for r equal to r2. If roots of indicial equation do not differ by an integer, then two independent solutions are given by this form of Frobenius method. But suppose two roots are equal or two roots differ by an integer, then how to find out the second solution? In every case we will always have one solution in this form, x raised to r into an x raised to n or an x raised to n plus r. We will always have at least one solution in this form, and second solution is also in this form in first case where r1 and r2 are different and they do not differ by an integer. But if we have equal roots or if difference is an integer, then our second solution can be different from this form. And if you recall, in the topic of higher order ordinary differential equations, we have discussed the method of reduction of order. Using that method, we can find out the second linearly independent solution if we are given the one linearly independent solution. If we are given the value of first solution or one solution of this type of equation, y double dash plus py dash plus qy equal to 0, then if you recall, we can find out second solution by this formula: y2 equal to y1 times e to the power minus integral of p with respect to x divided by y1 square integral with respect to x. So we can apply this method of reduction of order in this topic of Frobenius method also. If it is easy to integrate this quantity with respect to x, then we can use method of reduction of order in both of these cases. If roots are equal and roots differ by an integer, and if we are able to decide one solution, then second solution can be obtained by this formula, provided that integrals are easy. And integrals will be easy if our solution y1 can be expressed in some closed form. For example, if our solution is in this form, say y equal to 1 plus x square and so on, then we know that this is the Maclaurin series of 1 over 1 minus x. So this 1 over 1 minus x is called closed form of this solution, and if it is possible to write one solution in closed form, then this integral will be easy to evaluate and we will be able to decide this second solution. Now if there are some difficulties in evaluating this integral, then we have some another criteria also in Frobenius method, but recently in these two cases I am going to apply method of reduction of order to obtain the second solution. Here I have taken this example which was asked in GTU Summer 2022 exam, and here we will see that indicial equation has equal roots, and using method of reduction of order we will be able to decide second linearly independent solution. First solution will be decided by using Frobenius method and assuming that solution is always in this form if x equal to 0 is a regular singular point of given differential equation. So first we will prove that x equal to 0 is a regular singular point of this equation, and therefore this type of series solution is possible, and after that we will try to determine values of r and these coefficients, and then we will substitute them in this standard form of Frobenius method. So I have written this differential equation. It is not in standard form. Standard form means coefficient of y double dash must be 1. Therefore we have divided this equation by x times x minus 1, and we have this form, standard form. And if we compare this equation with y double dash plus px y dash plus qx y equal to 0, then this is going to be value of p of x, 3x minus 1 over x into x minus 1, and this is q of x. So that I have written here. And for a regular singular point we have to check whether x times px and x square times qx are analytic at x equal to 0 or not. So in the next step we multiply this by x and this by x square. So we have x times px equal to 3x minus 1 over x minus 1. This x will get cancelled. X square times qx equal to x square divided by x into x minus 1. So this x will get cancelled and we will be left with x over x minus 1. Now we can see these two are rational functions, and we know that rational function is analytic at all those points at which denominator is non-zero. Here we have x minus 1 in the denominator. So these two functions are analytic at every point except x equal to 1, and we are checking for x equal to 0. Therefore clearly both of these two are analytic at x equal to 0, and therefore by definition x equal to 0 is a regular singular point of equation number 1, and therefore by Frobenius method we can assume that equation 1 has at least one solution that we can represent in this form: y equal to x raised to r times sigma an x raised to n equal to 0 to infinity, or we can write in this form an x raised to n plus r, and here we will assume that a0 is not equal to 0. I have explained why we are assuming a0 as non-zero in previous lecture. Now we have to find out y dash and y double dash, and then we will substitute them in this equation number 1. Once we are sure that our solution is in this form, then our aim is to decide the value of r and these coefficients an. So for that we will substitute value of y dash and y double dash in the given equation. To write down first derivative, we will consider an as constant, and derivative of x raised to n plus r is n plus r times x raised to n plus r minus 1. That is our y dash. N will take the same value 0 to infinity. For second derivative, this quantity is constant. Here n plus r minus 1 will come again this x, and x raised to n plus r minus 2. So n plus r minus 1 an x raised to n plus r minus 2. And now we substitute values of y dash and y double dash in this equation, in given equation number 1, that is x minus x1 into y double dash plus 3x minus 1 into y dash plus y equal to 0. So that I have put here, and I obtain this expression, x minus x1 into y double dash 3x minus 1 into y dash plus y equal to 0. Next step is we multiply this summation by this quantity, which we can rewrite as x square minus x. So x square times this summation minus x times this summation. If I multiply with x square, then it will combine with this power of x, that is x raised to n plus r minus 2 into x square, and 2 will get cancelled, and we will have x raised to n plus r, and minus x, that is this will be multiplied with x. So we will have x raised to n plus r minus 2 and plus 1, that is going to be x raised to n plus r minus 1. So that I have written here. Same thing here, 3x is multiplied with this, and here power of x is 1, and here power of x is n plus r minus 1. So we will have x raised to n plus r minus 1 plus 1, that will be x raised to n plus r, rest of the things as it is, and minus of this summation, that I have written here, and plus this sigma n x raised to n plus r equal to 0. Now we check whether in every summation power of x is same or not. Here we have n plus r, here we have n plus r, and here we have n plus r minus 1. So to combine all these summations, we must have same power of x. So for that, here we can consider this quantity n minus 1 equal to some new variable, say m. Same thing for here. So for these two summations, I am changing the index. I am taking n minus 1 equal to m, and n is starting from 0. If I take n equal to 0, then m will start from minus 1, and n will be replaced by m plus 1. So you can see this will be converted in sigma m equal to minus 1 to infinity. This n will be replaced by m plus 1, so we will have m plus r plus 1. This n minus 1 will be replaced by m, so we have m plus r. N will be replaced by m plus 1, so we will write am plus 1. Here n minus 1 is replaced by m, so we have x raised to m plus r. Same thing here, n will be replaced by m plus 1, so we will write m plus r plus 1 here. A suffix n, that is a m plus 1, and this is x raised to n minus 1 is m, so m plus r, and m is starting from minus 1 to infinity. So these two summations will be converted in terms of new dummy index, which we have given name as small m. Rest of the things are as it is. So that I have written here, n minus 1 is taken as m, therefore n is m plus 1. If n is taking the values 0, 1, 2, then m is taking the values minus 1, 0, 1 up to infinity. So I have written changes in these two summations, and rest of the things I have written as it is. So I obtain this equation now. Now in every term power of x is n plus r, and because this is dummy index, we can again replace m by n also. So in the next term, I have not replaced m by n, but you can understand that whether I am writing m or n in these two summations, things are same because it is a dummy index. So instead of m equal to minus 1 to infinity, if I am writing n equal to minus 1 to infinity, or if I am replacing m by n, then also we don't have any problem. So let me replace m by n everywhere here. So I am writing n here. Instead of m, I have to write n. So here n plus r plus 1, n plus r, a n x raised to n plus r. Same thing here, instead of m, I have to write n because it is dummy index. There are no problems if I am writing m or n, x raised to n plus r. Now to combine all these summations, the range of index must be same. Here n is starting from 0, here it is starting from 0, this is n, and here also n is starting from 0, but these two summations are starting from minus 1. So what we can do is, we can write this summation as term corresponding to n equal to minus 1 plus sigma n equal to 0 to infinity and this quantity. Same thing here, and rest of the summations are as it is. So for that, first I have written the terms corresponding to n equal to minus 1 in these two summations. If I take n equal to minus 1 here, then you can see I will have minus 1 plus r plus 1, 1 will get cancelled and I will left with r, and I have negative sign here. If I take n equal to minus 1 here, I will have r minus 1. For n equal to minus 1, I will have a suffix minus 1 plus 1, that is a0, and this is going to be x raised to r minus 1, and minus sigma n equal to 0 to infinity, this quantity. So that I have written here, minus n equal to 0 to infinity, n plus r plus 1, n plus r, a n plus 1. So that quantity I have written here, and minus sign. This I am writing as term corresponding to n equal to minus 1, and because I have negative sign here, here also I have to write negative sign. So that quantity will be sigma n equal to 0 to infinity, n plus r plus 1, n plus r, a n plus 1, x raised to n plus r. That term is here, sigma n equal to 0 to infinity, negative sign, x raised to n plus r. Similarly, from this, if I take n equal to minus 1, I will have negative of r. For n equal to minus 1, I will have r here, this is a0, and x raised to r minus 1. So that quantity is written here, and this summation will be equal to this quantity minus sigma n equal to 0 to infinity, and this quantity n plus r plus 1, a n plus 1, x raised to n plus r. So that also I have written. So let me search for that quantity. For n equal to minus 1, I have this quantity, and for n equal to 0 to infinity, I have negative sign, and n plus r plus 1, a n plus 1 into x raised to n plus r. So that I have written here, sigma n equal to 0 to infinity, n plus r plus 1, a n plus 1, x raised to n plus r, and rest of the things as it is. And I have combined simultaneously. I have taken x raised to n plus r common, and you can see n plus r minus 1, a n, that quantity is here, 3 times n plus r a n, that is here, and this quantity minus a n x raised to n plus r. So here I have to write minus a n x raised to n plus r equal to 0. just a minute, this is plus sigma n x raised to n plus r, so I must write plus here, and therefore here also it is positive sign. So plus an x raised to n plus r sigma n equal to 0 to infinity, and these two we have already written. So for these two we have negative sign that we have written here. Okay, fine. Now here in these two terms we take a0 x raised to r minus 1 common and negative sign also common. So here we are left with r into r minus 1, here plus r, and now we have taken an common from these terms, and we have n plus r minus 1 plus 3 times n plus r plus 1 an, and I have combined these two terms. I have taken minus an plus 1 common, and this is, I have written this term first, n plus r plus 1 plus n plus r plus 1 into n plus r an plus 1 x raised to n plus r equal to 0, and I give this equation as number 2. So I have coefficient of x raised to r minus 1 and coefficient of x raised to n plus r, and right hand side is 0. So this is possible if and only if coefficients of x raised to r minus 1 and coefficients of x raised to n plus r must be 0. So first we equate the coefficient of x raised to r minus 1 to 0. So that means we must have this quantity r minus 1 plus r times a0 equal to 0. And we have assumed that a0 is non-zero, therefore we must have r into r minus 1 plus r equal to 0. This I can rewrite as r square minus r plus r equal to 0, and therefore r square is 0. That means we have equal roots. So this is the case that indicial equation has two equal roots. This is second case. We have double root, and that root is 0, 0. Now once we find out the values of r, which are the roots of indicial equation, now we compare the coefficients of x raised to n plus r on both sides, and because right hand side is 0, we must have this quantity in the bracket equal to 0. So that I have equated to 0, and then I have taken n plus r common here, and I am left with n plus r minus 1 plus 3 and this plus 1, and this negative sign is there, therefore I have taken this term on the right hand side, and simultaneously I have taken n plus r plus 1 common, and here I will have 1, and here I will be left with n plus r into an plus 1, and these summations are starting from n equal to 0 to infinity, therefore here also n will start with 0. And in the next step you can see this n plus 1 suffix is there, so I have to express an plus 1 in terms of an, and this is nothing but square of n plus r plus 1, that I have to divide by this quantity. This is going to be n plus r plus 2. So n plus r plus 2 plus 1 an equal to n plus r plus 1 whole square an plus 1, and therefore this quantity equal to this quantity divided by square of n plus r plus 1. N takes the values 0, 1, 2 and so on. This is the recurrence relation for the coefficients of our assumed series solution. Our assumed solution is sigma an x raised to n plus r. Now r is now 0, therefore we have sigma an x raised to n, and we are interested in these coefficients an now. For that we have developed this recurrence relation. Now we can obtain the first solution, or we can obtain one solution by taking r equal to 0 in this recurrence relation. So I am taking r equal to 0 in this number 3. I will have an plus 1 equal to n times n plus 2 plus 1 divided by square of n plus 1 and into an. and if I multiply these two, I will have n square plus 2n and plus 1, and if I expand this, it is n square plus 2n plus 1. Then, and I can cancel out this quantity. This quantity is nothing but square of n plus 1, and n plus 1 is 0 if n equal to minus 1, but our n is starting from 0, so no problem, we can cancel out square of n plus 1, and we will have an plus 1 equal to n equal to 0, 1, 2, 3 and so on. So we have very simple recurrence relation. Here if I take n equal to 0, I will have a1 equal to a0. If I take n equal to 1, I will have a2 equal to a1. Similarly, if I take n equal to 3, I have a3 equal to a2. Now a1 is a0, therefore a2 is also a0, therefore a3 is also a0, and so on. This means every coefficient is equal to a0, starting with 1, 2, 3 and so on. So now once we have value of each coefficient, we can write down this series solution. Our series solution is sigma. This we have assumed. This is the form of Frobenius series solution. Sigma an x raised to n plus r, and value of r is 0. If I take r equal to 0, I will have sigma an x raised to n, and an is a0 for every n. Therefore we have a0 x raised to n. a0 is independent of n, so we can take it outside summation, and we have a0 sigma x raised to n equal to 0 to infinity. This sigma x raised to n is nothing but this series 1 plus x square and so on. If you take n equal to 0, you have x raised to 0, that is 1. For n equal to 1, we have x. For n equal to 2, x square and so on. And this is nothing but geometric series with ratio x. Common ratio is x and first term is 1. Therefore this is equal to 1 divided by 1 minus x. And if you recall, in mathematics 1 course, we have seen that Maclaurin series of 1 over 1 minus x is sigma x raised to n equal to 0 to infinity. Therefore I can replace this by 1 over 1 minus x, and this a0 is arbitrary constant, so we can set a0 equal to 1, and we obtain the first solution as y1 equal to 1 divided by 1 minus x, and this is the closed form solution. Our series solution is a0 sigma x raised to n, and this we can represent in this formula in this closed form also, 1 over 1 minus x. Now this is the first solution of given differential equation using Frobenius method, and as I discussed in the starting of this lecture, that if we have closed form solution, then we can use method of reduction of order to decide the second linearly independent solution. For that I have to decide, or I have to check what is the coefficient of y dash in given equation after it is expressed in standard form, that is in this form. Here coefficient of y dash we have already obtained, it is px, and it is 3x minus 1 over x into x minus 1. We will require this coefficient in the method of reduction of order to obtain this second solution. So now I am trying to find out second solution using reduction of order, and this is the first solution. Px is 3x minus 1 over x into x minus 1, and if you recall that in the method of reduction of order, second solution is given by y1 times, in the integral we have e to the power minus px dx divided by y1 square. Whatever we obtain, that we have to integrate with respect to x. So first I will require the integral of this rational function px. So I have obtained integral of px first, and then I have used this formula to obtain y2. Now here you can see I have x into x minus 1, and both are linear factors, so I can use the method of partial fractions and I can represent this px in this form, something upon x plus something over x minus 1. And without using this method of partial fractions also, we are able to write down px in this form. We can rewrite this 3 into x as addition of 2x and x, and then we can see if I divide 2x by this quantity, I will have x cancel and I will have 2 over x minus 1. And if I divide x minus 1 by this quantity, x minus 1 will get cancelled and I have 1 by x. Now these two functions are easy to integrate. Integral of px equal to integral of this quantity plus integral of this. Two constant, integral of 1 over x minus 1 is log x minus 1. Integral of 1 by x is log x. Using the property of logarithm, I can rewrite 2 into log x minus 1 as log of x minus 1 square plus log x. Again, using the product rule property of logarithm, I can rewrite this as log of product of x minus 1 square and x. Now this is easy to integrate, so we will directly put integral px equal to this quantity. Second solution by the method of reduction of order is y1 times, inside the integral we have e raised to minus of integral of px divided by y1 square integral with respect to x. Px is, integral of px is log of x minus 1 square into x. This I have substituted here, negative sign is there. Y1 is 1 over 1 minus x, so that also I have substituted. And now if I take this quantity 1 over x minus 1 square in the numerator, I will have square of x minus 1. Here, using the property of logarithm, I can take minus 1 in the power of this bracket. And again, using the property of these two functions are inverses of each other. So we have e raised to ln alpha equal to alpha. Instead of alpha, we have x minus 1 square into x raised to minus 1. And this is equal to x minus 1 square raised to minus 1, that is x minus 1 raised to minus 2 into x raised to minus 1 into this quantity. And these two will be combined and will give us 1, x minus 1 raised to 0, that is 1, and this is integral of 1 by x. Integral of 1 by x is log x, and this is already there. Therefore, second solution is log x divided by 1 minus x. And once we have two linearly independent solutions, we can write down the general solution by taking their linear combination, c1 into y1, that is 1 minus x, c2 into y2, which is log x over 1 minus x. So in this way, if indicial equation has two equal roots, what we can do is we can obtain the first solution using Frobenius method, and if it is possible to write down this solution in closed form, or if it is possible to integrate this function easily, we can decide this second linearly independent solution by using method of reduction of order. And if it is not easy or comfortable to use reduction of order, then also we have another criteria to decide this second linearly independent solution that we will discuss later. So this is all about this session. In this session we have discussed that what is the Frobenius method in the case that indicial equation has two equal roots. If roots of indicial equation are equal, then how to obtain the series solution in Frobenius method. In upcoming lecture, we will discuss the last case, that if roots of indicial equations differ by an integer, then how to obtain the Frobenius series solution. So this is all about this session. I hope you like it. Thanks.